A uniform ladder of mass 12 kilograms and length 5.4 meters rests in equilibrium with one end on a rough horizontal ground and the other end against a rough vertical wall. The normal reactions at the wall and the ground are 36 newtons and 82 newtons respectively. Find A, the coefficient of the friction between the ground and the ladder, the coefficient of friction between the wall and the ladder, the angle the ladder makes with the ground. Obviously, to do this sort of question, you need to draw a diagram. So here we've got a wall and the ground. We've got the ladder. Makes an angle of theta. Both these are rough. The weight, 12g newtons, will be acting downwards here. Then here we will have a normal reaction, which will be 82 newtons. And here we have a normal reaction acting this way against the wall, which will be 36 newtons. Because they're both rough, there's friction. So there'll be a frictional force here stopping it slipping that way, which we'll call F1. There'll be a frictional force stopping it slipping down the wall, which we'll call F2. So, like all mechanics modelling problems, you need to draw a diagram. Right, what we will do first of all is resolve horizontally and vertically. So resolving horizontally. So what we've got going horizontally, we've got F1, and we'll need to subtract from that this force here of 36, which is the normal reaction between the ladder and the wall, and that will be equal to 0 because the whole thing is in equilibrium, and therefore F1 will be 36 newtons. Now if we resolve vertically, so that's going this way, we will have F2, this frictional force here going up the wall, plus this normal reaction here, which is 82, and then against that we will have, so take away minus 12g is equal to 0, which means that F2 will be 12g minus 82, which is 35.6 newtons. Okay, so carrying on. So just redrawing the diagram very quickly, and then we'll write down what we've already found. We've got F1 is 36 and F2 is 35.6 newtons. So the coefficients between the base of the ladder here and the ground, okay, we should know the system's in equilibrium, so limiting frictions, we've got F1 will be equal to mu1 R. We've got that mu1 will be F1, which is 36, divided by R1, which is 82. R1 was this, which will give me 0.439. So that coefficient of friction will be that. And then doing a similar thing for the coefficient of friction between the ladder and the wall. We're going to have that F2 is equal to mu2 R2. So mu2 will be F2, which is 35.6, divided by 36, which will give me 0.989, so quite a high coefficient of friction. Right, in the next part now, in the last part, we need to find the value of the angle here, theta. So I've put in the values of the two frictional forces. They've been written in. Okay, in order to do this, we will need to take moments about this point here. Now, I like to draw out a horizontal, this ladder here horizontally. So we have this first force here acting down at the center of the ladder because it's uniform. And because this angle here will be theta, because this one is theta, this will be 12g cos theta. So acting downwards here, we have a force of 12g cos theta, acting at halfway point, which is 2.7 meters. This is 5.4 in total. Right, well, now we have a force here, but it's actually acting at this point, but I've drawn it here so we can see it quite easily. This will be 36 sine theta. 36 sine theta. Okay, we can see that theta is equal to theta because we can use the concept of alternate angles. This force here is parallel to this one here. Right, now we have to work out what the component of this one would be. So in order to do this, I'm just going to make this little bit here a bit larger. So here we have the wall and the ladder and the frictional force. Okay, if we continue the ladder, we want to know what this force is going to be. If we continue the ladder, then these two angles will be the same. So if this angle is theta, this angle up here will be 90 minus theta. So both these angles will be 90 minus theta, but this are at right angles to each other. Okay, so if this is 90 minus theta, that makes this one theta, which will make this component here, which is 35.6 cos theta, because this will be the next to the angle. So we'll put it on here as well. Okay, and then we'll transfer it over to this diagram. It's acting at exactly the same point. This force and this force here are acting exactly at the same point, although I've drawn this one over here so we can see it nicely. So this will be 36 cos theta. Right, so taking moments, so the anti-clockwise moments will be 5.4, so it's force times distance, or distance times the force, times 36 sine theta, plus 5.4 times 35.6 cos theta, and then going clockwise we will have minus 2.7 times 12g cos theta, and as it's in equilibrium that's equal to 0. So summing this one, working out this one, 5.4 times 36 will give me 194.4 sine theta. And then doing 5.4 times 35 minus 2.7 times 12g, taking g to be 9.8. And then taking it to the other side will give me 125.28 cos theta. Taking cos theta underneath here, so we get sine theta over cos theta. And then we're going to have here 125.28 over 194.4. Now sine over cos is actually equal to tan. So tan theta is equal to this value here, and then theta will be tan to the minus 1 of 125.28 over 194.4, which will give me an angle of 32.8 to 1 degrees to 1 decimal place. Quite a shallow angle for a ladder. Okay, so this has been a video to show you how to resolve a ladder problem. I hope you've understood, and I thank you very much for watching, and if you're happy to, please subscribe to my channel.